Okay, so we'll start now. So in the previous class, we discussed about design of zip and cotter joint, and we taken up one numerical problem also on that. So I think I explained you the design procedure and ask you solve the problem. So now today we'll see. I don't know how many of you solved that problem. We'll see the solution first for that. Then we'll move on to the next one, that is knuckle joint. So here this is the given problem. Design a jib and cotter joint to carry a maximum load of 35 kilonewtons. Assuming that jib, cotter and rod are made of same material and have the following allowable stresses: sigma T 20 MPa, tau 15 MPa, and sigma C is 50 MPa. So in the design procedure, first you need to calculate what is X value. So that can be calculated based on the tensile strength. So first we need to find that X is nothing but the side of the square rod. So considering the tensile failure of the rod, so you get a equation X square into sigma T equal to the applied load, which is 35 kilonewtons. You convert the 20 into newtons, 35,000 newtons. So it should be equal to 20x square. From that you will get your X is equal to 41.8, maybe equal to 42 mm. Then once you got the X value, like what we discussed in the previous class, your B1 is equal to X only, and T is equal to B1 by 4. So that is, if you take a B, X is 42, then B1 by 4 is nothing but 42 by 4, comes out as 10.5, that may be rounded up to 12 mm. Then thickness of the jib as well as height and length of the jib head are taken as equal to the T only, so which is 12 mm, 12 mm. So these are the empirical relations we have to follow like this only. There is no failure criteria to find the length and the height of the jib head. Okay, right. So once you done that, then you need to find out what is the width of the jib and cotter in combinedly. So for that we need to consider the shear failure, and also we know that they are in double shear. So therefore the area of shear is 2 into B into T multiplied by the allowable stress will give you the shearing strength, and you need to equate this one to the applied load, that is 35,000. So from that you will get a B value, so which is going to be 97.2 mm. So let us say it is rounded up to 100 mm. Once you got this B value, then depending upon the number of jibs used in the joint, whether it is a single jib or double two jibs, you need to find out what is the individual width of jib as well as cotter. So in this particular one, he has given only single jib. So then the empirical relations for the width of the jib is 0.55 times capital B, which is 55 mm, and the width of the cotter is going to be 0.45 capital B, which is nothing but 45 mm. So once you got this, then what you need to do is you need to find out the other dimensions just by considering the failure of the, that is the thickness of the strap. So next one, so that we'll find using the failure of the strap ends. So for that we already discussed that the area of the strap end which resisting the tensile failure is going to be 2 into X into T1 minus T1 into T. So because why we are using T is because it is in double shear, you need to take it as 2. So it is 2 sides you have a strip, so you need to take 2 here. So therefore multiplied by sigma T will give you the value of the shearing strength. You need to tearing strength. You need to equate the tearing strength to the applied load, which is 35,000. So from that you will get your T1, that is length, thickness of the strap. So which comes out as, from this calculation, it comes out as 29.1. So which is equal to 30. So it may be rounded up to 30. Then once you calculate with this thickness, then you need to check for the crushing stress value, whether this crushing stress is with the values of T1 and T, whether the crushing stress induced in this cotter or maybe the strap is less than the allowable stress or not. We need to check that. So for that, so the applied load should be equal to the crushing area, which is nothing but 2 into T1 into T multiplied by sigma C. So from this you need to compute what is sigma C. So sigma C is nothing but 35,000 divided by 2 T1 into T. So we already calculated T1 as 30 and T as here we 12 mm. So if you substitute that 30 and 12, from that you'll get your sigma c is 48.6. So which is less than the allowable bending stress. Allowable bending stress is given as 50 MPa. So therefore here the individual stress is less than the allowable stress. Then we can say that the design is safe. Then after that you need to find out what is the length of the rod end. So considering the failure of the rod end in shear, so here it is in double shear. So you need to consider the double shear area, which is nothing but 2 into L1 into X multiplied by tau will give you the shearing strength of the rod end. So you need to equate that one to the applied load, which is 35,000. From that you will get L1 value. So from this calculation, L1 comes out as 27.7, maybe rounded up to 28 mm. Similarly, by considering the shear failure of strap end, you will get the length what you required for the strap end for avoiding shear failure. So again, the formula for that is 2 into 2L2 into T1. So we already seen this derivation. We got 2 into 2L2 into T1 multiplied by tau. So we'll give you the shearing strength of the strap end. Then that should be equal to your applied load. From that you will get your L2 as, from this calculation you got it as 19.4 mm. So which is maybe rounded up to 20 mm. So once you got that, then the L3 will be taken as 2/3 of X, which is nothing but 28 mm. And length of the cartridge is taken as 4X, so which is 4 into 42, which is 168 mm. So like this, you can find the dimensions of this Gibbon cartridge joint. So in this, there are some empirical relations what you need to remember. So because this is not available in the data book. So this joint is, the information about this joint is not available in the data book. So you need to remember those empirical relations. So then only you can solve this problem. Okay, right. So then what we'll do is, okay, another type of Gibbon cartridge joint is there. So okay, so I think the procedure is same here also like previous one. So I'm not going to discuss this one. Straight away we'll move on to the knuckle joint. The last one in this. So in this cartridge joint, the last topic is knuckle joint. So with this, I think we will complete this topic also. Maybe we left with only one unit, that is the last unit, that is springs. Anyway, so first we'll complete this, then we'll move on to that other topic. So here, what is the knuckle joint? I think better I'll show you one more time that video what I played to you during the first class. Okay, let me check with I have a video of that one or not. I think so once you go through that video, you have some better idea. Yes. Okay, so get sleeve cutter and Gibbon cutter. Knuckle joint is not there here. Okay, so then what I do is I'll take you to YouTube. So then you can see that. Yes. Sorry. Class level. I'll play one more time. Just watch it carefully.
Hello friends, here in this video we will see the design procedure for
Okay, so just I think you might have seen about that knuckle joint. In that video, clearly has shown what is knuckle joint, in what applications it is going to be used, and also what are the various parts of that knuckle joint, also how they are assembled, also has shown everything in that video. Okay, again, so here we'll recall them. So generally, see, this is not a quarter joint. Even though this is discussed under the topic of the quarter joints, there is no quarter in this joint. So that's why it is given a different name, knuckle joint. So in the name itself, you can see that quarter is not coming. So earlier in all those joints, you have a quarter is there, but here there is no quarter. And also all those joints, earlier quarter joints, if you take that, their axes are coincide with each other. If you take socket as spy-guard joint, or sleeve and quarter joint, or jib and quarter joint, whatever it may be. So in all those joints, the axis of the two rods which are connecting is coincide. Whereas in case of this knuckle joint will permit a slight misalignment in the axis of the rods also. So that's why this knuckle joint is used to connect two rods whose axis either intersect or coincide. So that means you can have a small angular misalignment is also permitted in case of this knuckle joint. So that is the difference. Used to connect two rods whose axis either intersect or coincide and lie in the same plane. But the thing is, those two axes should be lie on the same plane. Again, this knuckle joint is also used to transmit only axial loads only. This, like already told, it permits a limited, so that limited angular movement of rod about the axis of the pin. So that means a limited angular misalignment can be allowed in case of this knuckle joint. Then the typical applications for this knuckle joint is in that video. If you observe that, he has given automobiles, then robotics, then some other applications he has given. So in addition to those applications here, you can use these knuckle joints in this case also. Joints between tie bars of roof truss, joints between links of suspension bits, fulcrum of levers, joints between the links of a bicycle chain, joints in a valve mechanism of a reciprocating engine. So these are some more applications of this knuckle joint. Okay, so now we'll go for the design of this knuckle joint. Before going into the design of this knuckle joint, we should know what are the parts, then what are various dimensions of those parts also. So that we'll call it as a terminology or terminology which is used in case of this knuckle joint. So basically we have more 3 or 4, actually to be precise there are 4 parts are there. So this tapered pin is also there, maybe he has not shown that here. See, you can see that one is a eye end or eye, this part we call it as eye of the joint, this one. Then you have a fork, then you have a pin, this pin is there. So then for that you have a collar is there, one more component collar is there, and then one more taper pin is which is inserted here, that is column pin. See, in this view you can see that this is the tapered pin. So totally you have 5 components. So not only 5 components, you can have 5 individual components. So you have maybe 2 rods, okay, only one only. All those things are one only. So these are the components what will you what are used for to prepare this knuckle joint. Then you can see that this is the front view or sectional front view precisely, and this is the top view for that knuckle joint. So in that he has shown various dimensions for the joint. So now we need to identify all those dimensions. So first dimension out of all those things, the first dimension is going to be D. So you can see it here, D. So what is this D? D is the diameter of rod. So here again it is a diameter, it is a circular one. So like in your jib end, except in jib end, all other jib and cord joint, all the rods are circular in cross section. So okay, before that P is the applied load. You can see that here P is going to be the load, and also that is also axial load. So axial means the load is applied along the axis of the joint. So this is the axis of the joint, load is applied only here. So it cannot permit any eccentric load. Suppose if this is the axis of the joint, the load is applied here, so I cannot analyze that one. So this joint is not permitted that one. So always the load should be an axial load. So maybe it may be tension or compression, but it should be an axial load. So that is the first P, load carried by the rods. Then D is the diameter of the rods here. Then next D1. So D1 is nothing but the enlarged view or enlarged diameter. The enlarged diameter of this rods only. Here this is D1. This dimension or this dimension is the enlarged dimensions of the rod D1. So see here, don't confuse here. These are capital letters. Capital D is the diameter of the rod, and capital D1 is enlarged diameter of the rod. Then you have small d is there. So small d is diameter of the knuckle pin. So we'll call this pin, whatever this pin is there, this one we'll call it as a knuckle pin also. Then the diameter of this pin we'll take it as small d. Then small do, outside diameter of eye or fork. So now let's see here, this is your fork, or this is the fork. Here if you take a section here, section across this one, this is the section what you are going to get. So in this you need to take, where is DO? DO is nothing but outside diameter of eye or fork. So see, you can see that here clearly has shown that this one has DO. DO is outside diameter of this. Okay, from the here you can see that from this you can see that that is the outside diameter of eye or fork. So that means this diameter. Then you have DI. Okay, instead of DI, you are taking it as D1 only. So you can take that one as D1, diameter of the pin head. So here you have a pin here. This is the pin, and this is going to be the head of the pin. This diameter he has taken it as D1. Then next one is A, thickness of each eye of the fork. So here this is the thickness. So here he has shown, where he has shown that A value. So you can see that here This is going to be the thickness, or else here you can take this one as the thickness. This is going to be the A. That is the dimension is A, thickness of eye of the fork. Then B is thickness of eye end of the rod. So now it is corresponding to the rod. So you can see that eye end of the rod is going to be, this is the thickness here. You can take this one. So this is going to be the B value. This dimension is going to be B. This diameter is capital D we are taken. So then this is enlarged diameter also there. So this is I think D1 only. So in that you have again your D. So this is going to be B here. That is thickness of eye end of the rod. Then you have X, distance of center of fork radius R from eye. So here before that this is the fork radius R. Fork radius is R. So now this X is nothing but, so here you have the radius center of that fork radius here center here from this point to this point. So that will take it as X. That is distance of center of fork radius R from I. So this is the starting point of I. So this distance is going to be X. This distance is X. Then you have the permissible stresses. Sigma T is permissible tensile stress for all parts. So assuming all parts are made of same material, so therefore the sigma T is same for all the parts. Then similarly you have permissible crushing stress for all the parts, and also you may have sometimes permissible shear stress also, tau also there, because if you take this pin, the pin is in a shear, so we need to consider permissible shear stress also. I think that is okay. It is there here. Permissible shear stress for all parts. So we'll take that one as tau. Okay. So now with the terminology, we'll go with the design procedure. So before going for the design procedure, so if I draw the free body diagram for these three parts, or for of course for these three parts, these are the three major parts. So if I draw the free body diagram, based on the free body diagram, I can easily identify what are the various types of failures for those components. So now the free body diagram will look like this. So this is the free body diagram of the fork, and this is the free body diagram of the rod or eye end, and this is that knuckle pin. So here, since it is subjected to P for equilibrium, here this pin is in contact with this one or in connection with this one here. So here I have a reactions, here P by 2, P by 2. So for equilibrium, this should be equal to this. So therefore here it is P by 2, P by 2. Because it is symmetric, I can take here the reaction is same. So therefore the load or the reaction here it is P by 2, here also it is P by 2. Similarly for the spin, so we need to represent, so this is the reaction on this collar. So fork, if we come to the pin, the reaction should be in opposite direction. So you have to take it as P by 2 and P by 2 here. Then coming to here, this is the rod. So here it is subject applied force is P. Then here only you have a contact with this pin. So therefore along this edge there is a reaction, but instead of taking that one as a distributed one, we'll take it as a point force. So then that should be equal to your applied force. So P here, the same thing if I take that one on the pin, it should be in the opposite direction like this. So therefore this is going to be the free body diagram for the three parts. So now we can clearly see that here this rod end is subjected to a tensile force. So that means D can be estimated based on the tensile failure. Then here even this one is also subjected to only tensile force. So but here you have a slot is there, a hole is there. So you need to consider that hole dimension. Based on that only you can calculate the D1. Then if you look at this one here, it is subjected to a shear here and here, double shear it is subjected to. So this pin dimensions can be find out based on the shear failure. Similarly, if you come to the fork here, so this here rod is again, so what like here, you have to follow the same criteria, tensile failure. No need to calculate here. Since we already calculated here, this D is same, so no need to calculate this. But here, these dimensions are calculated again based on the tearing failure across the slot. So those failures now we'll see one by one. first, failure of the rods in tension. First, what we consider is failure of the rod in tension. The rod may fail in tension due to the tensile load P. So for that, your equation is the applied load P should be equal to the tensile strength of the rod. Tensile strength of the rod is nothing but area of the tensile rod, area of the rod multiplied by its tensile strength, that is sigma t. So area is going to be 5 by 4 capital D square, because D is the diameter we are taking. Since it is a circular cross section, area is going to be 5 by 4 D square. The D is capital D here into sigma t. So that should be equated to your load P. From that you will get your equation for finding out this D value. So area resisting the tearing of the rod is 5 by 4 D square. Then tearing or tensile strength of the rod is 5 by 4 D square into sigma t. So now if we equate that one to P, so from this equation, sigma t is given to you and applied load is known to us. So we can calculate this D value from this. That is, the diameter of the rod is estimated based on this equation. So the enlarged diameter D1 of the rod near the joint is determined by the following empirical relations. So here the D1, that is the enlarged portion of the rod, is taken again based on empirical relation only. So that is, I think these relations are there in our data book. I think if you open our data book, they might be given in the data book. So let me open the data book and we'll see whether these are given in the data book or not. So open, if you have a data book, you also open your data book and open for me it is chapter number 7. Those who are having the latest book, latest edition, for them there is a unit 8. So you can see that he has given the knuckle joint in the data book. Earlier you don't have a quarter joint. That Gibbon quarter joint is not there in the data book, but this knuckle joint is available in the data book. So in that, the first one, okay, so first we'll see whether he has given the proportional dimensions or not. Yes, he has given last one. So if you refer our data book, in the data book, first he has given the desired particulars and equations. So for the knuckle joint, he has given the equations, load carrying capacity on the basis of A, tensile strength of the solid rod, B, shearing strength of knuckle pin, C, tensile strength of single eye, shearing strength of single eye D, E is crushing strength of single eye, like F, G, H. Up to H he has given the equations. Below that he has given the usual proportions of our knuckle joint. So that he has given, but what he has given it is small d1 is equal to small d, small d2 is equal to, here the thing is, he has followed the different notations. So here I taken the capital D's, so he has taken the small d's only for all those things. So don't confuse with those notations. So whatever, he has given the figure. So if you are familiar with, if you look at it in the figure, you can easily find out what are those dimensions also. So capital D, instead of capital D, he has used the small d, and also instead of D1, maybe he follow the some other values, some other proportions. So that's why you need to take it as anyway. So that he has shown D1 as 1.1 D. That proportion he has shown it here also in the diagram. If you refer the diagram, that is the enlarged diameter of the rod. He has shown it as 1.1 D only. So that also we are taking the same thing here. Then similarly, R is given as the radius of fork. He has given it as 1.2 D. And those proportions are given here. D1 is equal to D, D2 is equal to D, D3 is equal to 1.5 D, T is equal to 1.25 D, T1 is 0.75 D, T2 is 0.5 D. I don't know in a new edition how they are given these notations, but as per this old edition in the sense it is a third or fifth edition, I think. In this one, he has used all small d parameters only. So it doesn't matter what is the notation, what is the symbol you are using, small d or capital A, as long as if you are describing the given dimension, it doesn't matter whether you are using capital D or small d. So, but only thing is you need to mention here, like I said, diameter of the rod is capital D. I denoted diameter of the rod as capital D in my presentation. Whereas in case of this design data book, he has given the diameter of the rod as small d. So you mention like that and you can solve the problem. There is no issue. So you have all these formulas in the data book. Okay. So then only thing is the notation is different. That is the only thing. So it doesn't matter. So notation is different means here we are describing what we are using. There he is describing what he is using. So that means only thing is you need to understand how you need to use those formulas to solve those parameters. So for that also, as far as this knuckle joint is concerned, it is straightforward. So what you have to do is, you first identify what are the notations, then you take equation from A to H, whatever equations he has given. So you follow in that order only, A to H, you will get all those dimensions. Okay, so then I think if you have a data book, you can follow that. So I'll follow the notation what I am giving here. Accordingly, we'll discuss the design criteria for these things. So first step what we discuss is we'll find the diameter of the rod by considering it is tensile failure, and the equation for that it is 5/4 d square into sigma t is equal to p. From that you will get a d value. Once you got this d value, that is the diameter of the rod, you can find the enlarged diameter of the rod by using this empirical relation. So the same thing, the data book also has given the same thing, but only thing is it has used a different notation. So be careful about that. Then the shearing failure of the pin. So like already told, the pin is in double shear. You need to calculate the double shear area. The pin is subjected to double shear. Then the shear area. So we know that the pin is also circular here. So therefore the area of the pin is 5/4 d square. Here we are using d is the diameter of this knuckle pin. Then you need to multiply that one by 2 because it is in double shear. If you multiply this one by tau, you will get the shearing strength of here the 2 is missing. You need to take 2 also here. 2/5/4 d square into tau will give you the shearing strength of the pin. So from that, okay, here also it is missing. So don't miss that here. Equating to that, you will get from this you will get the diameter of this knuckle pin. So the small d. So here what is the dimension he has taken? Let me verify that also. So B equation is B has given the same thing in equation B. If you look at in the data book, equation B is shearing strength of the knuckle pin only. So we are also considering the same thing only, shearing strength of the knuckle pin. He has given it as 2 into 5/4 into d1 square into tau. So here we are considered D, he has considered it as d1. That is the only difference. So using this relation, you can find the diameter of the it's not diameter of the rod, it is the diameter of this knuckle pin is calculated. So that means first equation is A is used for to determine the diameter of the rod. Then you can use the same relation, empirical relation 1.1 times the D, so that you will get the enlarged diameter of the rod. Then after that we are using shearing failure of the pin to determine the diameter of the knuckle pin. So for that this is the equation. Then the standard proportions of diameter of the pin is follows. So D is equal to D. So what it means here, your diameter of the rod and the diameter of the knuckle pin should be equal. So I think in the data book also similar the thing is given, D1 is equal to D. If you go for that last one, usual proportions of knuckle joint, what he has shown it is D1 equal to D only. So D1 equal to D only. So here also we'll use the same thing here. So then we need to consider the crushing failure of pin in I. So that means here this is the pin which is inserted into both this is the I end and this is the fork end. So now if I consider the crushing failure of only this portion of pin, so then what I'll get from that? So from that I'll get this B dimension. So we'll see that now. So the compressive stress between pin and the eye. So here this is the pin and this is the eye. So you have to take the compressive strength is nothing but the area, compressive area multiplied by the compressive stress. So here this is the formula. See here, this is the B value, and the other dimension for this pin it is D. So B into D is going to be the crushing or bearing area. Then load is applied is P divided by sigma D, P divided by B into D will give you the sigma C value. So now here we are not, okay, so based on that allowable crushing stress value, we can calculate this B value. So that is what we can calculate. So then similarly, even if you want to calculate the crushing stress in the fork, so now that means here this is the bearing area or contact area between the pin and the fork here. So this is the area. So this much portion you have to take. So here it is A and here also it is A and the diameter is D. Then the area is going to be 2 times A into D. So that also should be equal to the applied force. So therefore sigma C is equal to P by 2 into A into D. So D is already calculated. Using this relation we can calculate this A also. So now you can compute the A value. So then next what we'll do is we can check for bending stress of the pin. Generally we won't check for the bending failure. Anyway, we'll try to see the analogy here. So we know that when the pin is tight in the eye and fork, failure occurs due to shear only. On the other hand, when the pin is loose, like in case of carter also we discussed, whenever there is a clearance is there, that will cause the bending. So here also if the pin is tight, then there is no issue of any bending failure. But if the pin is loose, then it is subjected to bending moment. So here you can see the figure here, because of that loosening, so there is going to be bending moment. So then it is subjected to a load something like this. It is assumed that the load acting on the pin is uniformly distributed in the eye, but uniformly varying on the two parts of the fork. Maybe this is only one of the assumptions. You need not to say it is something like this, or you can assume something like this also. There are point forces also. Only thing is, this is an approximate estimation only. It's not exact, because it is saying that it is assumed that load is acting on the pin. One side is assuming uniformly distributed load, the other side is taking it as a uniformly variable load. So like what we did in case of carter, here also the same assumption. This side it is a uniformly varying load, this side it is a uniformly distributed load. So now to find out the bending failure, what you have to do now is you need to draw the bending moment diagram for this. So for this distributed and variable loads, then from that you need to identify where is the maximum bending moment. So then once you got that maximum bending moment, that maximum bending moment divided by Z will give you the sigma B value. So where Z is the section modulus. We know this is a circular cross section. For a circular cross section, Z is going to be what is the value of Z? Z is nothing but your I by Y max. Z is I by Y max. So I is for a circular cross section, it is 5 by 4, 5 by 64, D power 4 divided by Y max, it is D by 2, then in that case it is 5 by 32 into D cube. 5 by 32 into D cube is going to be your Z value. So now I got a M value and I got the Z value. From that I can compute the sigma B. So now we need to check for whether the sigma B is within the allowable limit or not. So for that, here we already calculated these dimensions. What is A and what is B already calculated. So you can easily verify that also. So here, if you use those parameters, so like I said, this is the Z value, 5D cube by 32 is the Z value. So and this is going to be the maximum bending moment for this. If you draw the bending moment diagram, so from that you will get the maximum bending moment is like this. So now using this relation, sigma B can be find out. So then the next one is the tearing failure of I across that slot. Wherever you have a slot is there, then we will consider that tearing failure or tensile failure of the rod, so that you can estimate the dimensions there. So those dimensions are here, D0 and D. D is already evaluated, so only this D0 can be determined from that. So now From this, you can clearly see that the area is going to be B into D naught minus D multiplied by, and the given load is, it is subjected to only P here. Or else in the section we also can clearly see that this is the area which is resisting this tensile failure. This area and this area. So now if I take that section here, so this total outside diameter, this diameter is D naught. Then the inside diameter from here to here, it is small d. So then this distance, at this distance should be equal to total d minus d naught minus d. So that is this one. And then in this direction, that means this dimension, it is equal to b here. So this dimension is b. So then we get b into d naught minus d is going to be the area which is resisting this tensile failure. So then if you divide that one p by b minus d naught minus d, so you'll get your tensile stress. So we know the allowable tensile stress. From this equation, you can find out what is d naught. You can find out d naught value. So this is how you can find d naught using the tensile failure of I. Then similarly, shear failure of I. So here earlier you can see the I may fail in two ways. This is the tensile failure. So means across the section, across the diameter, it is failing something like this. Now you have a shear failure also there. So shear failure is now look like this. Only this portion is coming out here on either side. So you can see that here. So that means shearing is here means it is in double shear. Or in this view also you can see that it is shearing here. So it is in double shear. So then this distance what he has taken it as d naught minus d by 2 approximately. It's not exactly, it is an approximate because we cannot exactly estimate it where it is going to shear. So exactly the symmetric or not. So therefore in that case it is taken it as an approximate value which is d naught minus d by 2. Then the other dimension is b. So therefore you get b into d naught minus d divided by 2. Since it is in double shear, you need to take twice here. So p here. So from this you will get the expression for tau, which is nothing but p by b into d naught minus d. So here we already know all these parameters. We already estimated b, already estimated d naught and d. So here what we will only do is we will check for this tau, whether this tau is within the allowable limit or not. If not, you need to modify these values according to this equation. Then similarly we need to consider, okay, this is already done, tensile failure of the fork, we already calculated this. Fork is a double I and as a figure it is applicable to the fork except the dimension B, which can be modified as 2A in case of fork. Okay, so earlier we have seen the rod, I think it is, okay, it is I. These two are the failures of the I's. Now we'll go for failure of fork. So here also it is also failing in similar manner to the I end of the joint. So but only thing here is the dimension here we are taken as A. Earlier we had taken the dimension as D naught and D, B. Here we are taken it as 2A. So that is the only thing here. Then the area is going to be, see here, this B will be replaced by, here this B will be replaced by 2A only. So we have top end and bottom end. So therefore this is going to be the area which is resisting failure. D naught minus D into 2A is going to be the area which is resisting the tensile failure. So then P divided by this one will give you the sigma T. From this we know the sigma T value. So then we can calculate the A value here. So then shear failure of the fork, same manner. So we'll approximate this one as D naught minus D by 2. Then multiplied by 2A will give you the shearing area. So from this again what you have to do is you can check for the shearing strength of this fork end. So this is how you can use the parameters of different failure criteria to determine various dimensions of this knuckle joint. So to be summarized, the design procedure for this knuckle joint, the first step what we need to do is, first we need to calculate the diameter of the rod by considering the tensile failure of the rod. So for that the equation is P is equal to 5 by 4 d square into sigma t. So where d is the diameter of the rod end. Then the second step is we need to calculate the enlarged diameter of each rod by using the empirical relationship d1 is equal to 1.1 d. Then third, we'll calculate the dimensions of A and B by empirical relations A equal to 0.75 d and B is equal to 1.25 d. So those things are given in our data book also. You can use these empirical relations. So once you can use these empirical relations, then what you have to do is by using these dimensions, you need to check for those failures. So whatever failure criteria we discussed, that is tensile failure as well as shear failure, you need to check for those two failures, whether with these dimensions of A and B, whether it is safe or not. So you need to check that. So then only you can finalize these dimensions A and B are correct. Then calculate the diameter of the pin by considering the shear or bending failure of the pin. So this is the equation which is you will get if you consider the shear failure of the pin. Of course, here 2 is there. I am missing everywhere here. 2 times 5 by 4 d square into tau. That is the equation for the shearing strength of the pin. Or if you consider bending, this is the equation. Either you can use this equation or this equation to find out the diameter. But the thing here is, if you use this equation, you need to check for the bending stress. Or else, if you use bending equation, you need to check for the shearing strength. That is the thing what you need to do. Since you have two criteria to finding out the diameter, what you have to do is, if you use only one of those criteria, you need to check for the remaining criteria. That means bending stress. Suppose if I use shearing as the failure criteria to determine the d value here, once I got the d value, I have to use the d here. In that, I need to check for whether the bending stress is within the allowable limit or not. Then calculate the dimensions d0, d1 by empirical relations. Again, these things. d0 is 2d and d1 is 1.5d. Then once you've done that, what you have to do is you need to check for crushing and shearing stresses in I of the following I. So these are the equations for those values. Then similarly check for tensile and crushing and shearing stresses in the I also using these relations. So this is how you can design this knuckle joint for a given axial load. So that means first what you do is, like I already told, if you pick the values from the empirical relations, then you need to check for the individual stresses, whether the individual stresses are within the limit or not. If they are within the limit, okay, whatever value you have picked from the using empirical relations, that is correct. You can find out the those are the values. So then you can say that your design is safe. But if with those empirical relations, whatever dimensions you got it, they are for those dimensions, if the stresses are not less than allowable stresses, then you need to modify again those parameters. Okay, so that's it. So this is how you can design this quarter joint. So I'll go back again and I'll tell you the procedure again one more time. We'll recall it or we'll summarize it. So first you need to calculate the diameter of the rod using the tensile failure of the rod. Then using the empirical relation, you need to calculate what is the enlarged diameter of the rod. Then from that, after that, what you need to do is you need to pick the A value and B value based on these empirical relations only. Of course, these are there in the data book also. Then you need to calculate by considering only, first what we'll do is we'll fix to this one. We'll consider the shear failure of the pin and we'll find out what is the diameter of the knuckle pin. Then we'll check for the bending stress. So since we have picked this A value and B value, then we'll pick D0 and D1 also using empirical relations only. Once you pick all these parameters, you need to check for tensile, crushing and shear stress for both in fork as well as I. Okay, so here it is. It is a fork, not I. Second one is for, these are the equations for fork, not for I. Maybe typing error here. So you need to take these equations. So you need to verify that whether these three stresses are within the given allowable limit or not. Okay, so that is how you can design the joint. So then what we do is, still we have 10 more minutes time. So what we'll do is, so just note down this problem and you try to do this. So using data book, try to find the solution for this. And then upload within I think within 10 minutes you can do that. So you try to do that and upload in the class. note down the problem and try to use your data book to solve this particular problem.
Sir, sir,
చెప్పమ్మా.
sir, allowable stresses ఎలా కనుక్కోవాలి సార్? Allowable stresses sir.
స్ట్రెసెస్ ఇవ్వలేదు కదా ఇటు దీంట్లో,
సార్
ఇవ్వలేదు కదా నీకు.
ఎస్ సార్.
నేను కావాలంటే ఇంటెన్షనల్ గా ఈ ప్రాబ్లం సెలెక్ట్ చేశా, ఎందుకంటే నేను ఇంతకుముందు మనం చెప్పాం కదా, ప్రాబ్లంలో నీకు ఎలవబుల్ స్ట్రెసెస్ ఒక్కోసారి ఇస్తాడు, ఒక్కోసారి ఇవ్వడు, వాడు ఇష్టం. ఎగ్జామ్ లో నువ్వే డిజైన్, నువ్వే డేటా ఉపయోగించి మెటీరియల్ ప్రాపర్టీస్ తీసుకోవాలన్నా కదా. సో కరెక్ట్ గా క్వశ్చన్ చూడు ఏమిచ్చాడు, డిజైన్ ద జాయింట్ అండ్ స్పెసిఫై ద డైమెన్షన్స్ ఆఫ్ ఇట్స్ కాంపోనెంట్, సెలెక్ట్ సూటబుల్ మెటీరియల్స్ ఫర్ ద పార్ట్స్. ఉన్న పార్ట్స్ కూడా మెటీరియల్ నువ్వే సెలెక్ట్ చేయాలి.
ఓకే సార్.
సెలెక్ట్ చేస్తే మెటీరియల్ ఎలా సెలెక్ట్ చేస్తావు, బేస్డ్ ఎలవబుల్ స్ట్రెసెస్ సిగ్మా టి, సిగ్మా సి అండ్ టౌ. ఈ వాల్యూస్ బేస్ చేసుకొని యూ కెన్ సెలెక్ట్ ద మెటీరియల్ materials for the all the parts, right? So I'll show you this how we can select that parts. The rods are subjected to tensile force, therefore yield strength is the criteria for selection of the material of the rod, right? So whenever you have a tensile test, so in tensile test you will get the yield strength, so therefore you have to choose yield strength as the criteria for selection of materials. The pin is subjected to shear stress and bending stresses, therefore yield strength is also criteria for the material selection for the pin. Okay, then on strength measures, the material for the rods and pin will be selected as plain carbon steel grade 30 C8. SYD is 400. So if you open the data book, in the data book, if you see this 30 C8, so only thing is, only point what you have to remember here is, so the material are selected based on yield strength, because we are not doing any plastic analysis here. We are doing only the analysis within the elastic range. So therefore, you have to choose yield strength as the criteria for selection of the materials for all the things, whether it is a fork or a eye or maybe pin. For all those things, you have to select yield strength as the criteria. So if you have yield strength, then what we'll do is we'll use the carbon steels only for the components. So then in that particularly here in this particular problem 30 C8 is selected. So don't assume that always you need to take only 30 C8. What you can do is you select some other component. So but it should be a steel or some other grade carbon. That is the only thing. So if you choose 30 C8, then further 30 C8 SYD is 400 Newton per mm square. If you choose some other component, then you have to take the corresponding SYD value only. Then it is further assumed that yield strength in compression is equal to the yield strength in tension. So most of the ductile materials, this assumption is valid. If the material is brittle, then only your strength in compression is more than strength in tension. For all the ductile materials, the strength in compression is same as strength in tension. So you can assume that. So in practice, the compression strength of the steel is much higher than its tensile strength. So here the assumption is just taken like this. So we got SYD. The SYD is nothing but if you want to select some factor of safety, then you can select factor of safety also. If you use factor of safety, then your allowable tensile stress is nothing but SYD by factor of safety. You will get sigma T. Then if follow the failure criteria, failure theories what we have discussed. So if SYD is the strength, then what is the shearing strength in yield? SYS, that is nothing but if you use maximum shear stress theory, it is going to be 0.5 times SYD. Or if you want to use distortion energy theory, it is SYD by root 3. So from that you will get your tau, allowable shear stress. Of course, if you use factor of safety, you need to apply that also. You will get SY, then you will get allowable shear stress. Then there is a relation for a given material. There is a relation between sigma and sigma c. You can find that also. Okay. So in stress analysis, the effect of stress concentration is neglected. So you need to take that also. So we are assuming that there is no stress concentration, but to counter the what you can say to justify this statement, that is, if I am assuming there is no stress concentration means actually there are geometric irregularities are there, rules are there, all these things are there. Definitely there is a stress concentration, but I am not ignoring that. So I am ignoring it. Why? Because I am ignoring it is I am considering a factor of safety of 5 here. So once you consider the factor of safety as a 5, then these are the relations to find out your sigma T, sigma C and tau. So sigma T is SYD by Fs. SYD as given as 400. 400 by 5 is 80 MPa. Sigma C. So we made the assumption. What is the assumption we made there? The strength in tension as well as compression is same. So therefore your sigma T, sigma C should be same. Or else sometimes we take, generally we will take sigma C is 1.2 times sigma T. So whatever you assume it, you need to state that in the problem. That is the thing. So tau is nothing but SYS by Fs. Here you use the maximum shear stress theory. Your SY is 0.5 times SYT, then divided by a factor of safety will give the allowable shear stress. So like this you need to do it. So that means what you have to do is first you have to pick the material, then you need to apply some factor of safety. So then based on that you need to estimate what is sigma T, what is sigma C, what is tau. So once you done that, then remaining procedure will get in the data book. Even these material properties also you need to pick from the data book only. Yield strength you have to pick from the data book. So if you go for that second unit in the data book, so there material properties are given for all the materials. So you choose a particular material generally which is used for this knuckle joint. Then based on that you need to identify the values. Okay. Anyway, it is now 10:30. We'll stop now. Maybe we'll discuss this in the next class.
Okay, sir.
Okay.